titrations are just acid-base mixtures, just like we've been doing. And so actually the titrations are no different than the calculations that we've covered so far. The only difference is, with the titrations, these are going to be a little different than your Chem 1A titrations, because what we're going to do is we're going to generate a pH curve. The pH curve plots the pH versus milliliters of titrant. And typical pH curve, we have different ones, but let's take a look at strong acid being titrated with a strong base. Sodium hydroxide and HCl. Over here, we'll have milliliters of strong base, and so this is what you'd put in the burette. In the flask or the beaker, whatever you're using to titrate, you'll put in the acid. And so we're at 0 milliliters of sodium hydroxide. We just have the acid. And the pH is going to be very low. pH is going to be 1-2 region, depending on how concentrated you make the acid. And so our starting initial is just strong acid. And so this is the first point. Well, if we want the pH of a strong acid, we would just figure out the concentration of hydronium in that solution, and we can get it. Then the titration starts, and you start adding sodium hydroxide, or whatever strong base you're using. Let's just pick one, like HCl and sodium hydroxide. So we start adding sodium hydroxide, but it's not enough to neutralize all the acid. So what we have in this region is called the excess acid. And so in step 1, you would react the sodium hydroxide. The sodium hydroxide is completely consumed, and you have excess acid left over. If you have excess acid left over, it's HCl, and so the pH is going to be quite low. It's not until you've neutralized practically all the acid. When we neutralize practically all the acid, then the pH rises. It's a very steep rise here. And this rise happens within 1, 2, or 3 drops. Within 3 drops, you're from here to here. And it turns out, now we're up at pHs around 10, 11, 12. And then right in the middle of this rise, is what's called the equivalence point. The equivalence point is what? Again, the equivalence point is when you've neutralized. You have equal amounts of acid and base, you've neutralized it completely. And so at the equivalence point, we just have salt and water, sodium chloride and water. And so the way we do this is, initially we have strong acid, and then as we go along here, sodium hydroxide, sodium chloride, and water. As we go along, it depends on what's in excess. So if we have excess HCl, we're going to have excess HCl here, no more sodium hydroxide. And sodium chloride is not going to impact it, so there's no common ion effect if we have an HCl sodium chloride solution. And so an example of something like this is, let's say we started off with 0.100 molar, but the sodium hydroxide, we've only neutralized half of it. If we only neutralize half of it, then the sodium hydroxide, being the limiting reagent, is going to be completely consumed, and we're going to be left over with half of our HCl unreacted. And that's going to be converted, the other half is going to be converted into sodium chloride, which shows liquids. So I skipped a change here, but the change is complete because this is a, do you know what K is for this reaction? You say complete because K is quite big, and we say that K is how big? No.
Very large?
No. The scale, use that qualitative scale I talked about earlier. last time.
Wait, Professor, you did the HCl plus sodium hydroxide, that is when it's at the equivalence point?
No, this is called the half equivalence point, because I've added half the required amount of sodium hydroxide to neutralize it. At the equivalence point, it would be full, but this is called the half equivalence point.
So that would be below that.
Right. The half equivalence point is if the equivalence point takes this many milliliters, you take half of that, and this would be the 1/2 equivalence point here. And so we're just saying, you know, where are we at in terms of. And so at the half equivalence point, we've neutralized half the acid. So we went from 0.1 to 0.05 molar. The pH is still going to be very low. And then sodium chloride has no impact on that. Even though it's a conjugate base, you know, this is an acid that's conjugate base. This is not a Henderson-Hasselbalch buffer. Why? This is not a Henderson-Hasselbalch buffer because it is a strong acid. And, but this is what we call the half equivalence point, and this reaction, you know, we don't have to worry about back and forth equilibrium. You know, we can have a 0 in here because K is I didn't write it. Is it in your notes? I didn't talk about it. Well, since we're in chapter.
Very, very large. Very, very, very large.
Yeah. That's it. This is very, very, very large. That's what I was looking for. Also, I did talk about it. Well, strong goes at completion. That's another way of saying it. And so here at this point, you know, we take the pH of 0.05. Well, it's going to be a little bit higher, but not much higher. It's still quite concentrated HCl, right? It's not until we get to the equivalence point that the pH is going to skyrocket up. And so this is what the half equivalence point looks like. What does the equivalence point look like? The equivalence point looks like where, well, I'd have to add what we call one equivalent. Well, one equivalent will be 0.100 molar for sodium hydroxide HCl. It's a 1-to-1 reaction. And so this is a stoichiometric, meaning that these are going to go to 0, and I'm going to be left with 0.100 molar sodium chloride. Well, 0.100 molar sodium chloride, what's the pH of that? The pH of 0.100 molar sodium chloride is 7. This is pH 7 here at the equivalence point. Okay, then immediately, if I keep adding sodium hydroxide, this is one of the major differences between a Chem 1A and Chem 1B titration. In a Chem 1A titration, you would stop here. In a Chem 1B titration, we keep going. We keep going until things stop changing. And so immediately, if we go past this, what's going to happen is the pH is going to jump up because we're going to have excess sodium hydroxide. The sodium hydroxide is going to raise the pH, sodium hydroxide being a strong base. And so another point we can get is here, you know, if we add 0.150 molar of sodium hydroxide, then we're going to have 0.050 molar left over. Well, that's going to give a fairly high pH, and that's called the 3/4 equivalence point here. 3/4 equivalence point, and we go beyond because we want to see what happens here. But at the 3/4 equivalence point, we're going to have some excess sodium hydroxide in there, and actually beyond that, in fact, right when you go past the equivalence point, we'll have some excess sodium hydroxide. So basically, most of these we just do, you know, step 1, not really worry about KW. The only time we really worry about KW is near the equivalence point here. Here you'd have to do a step 2 to get the pH. And so we just take the strongest acid, react it with the strongest base, and then we get it. Well, what we do here is we just carry on. So we go 3/4 and then double the equivalence point. We'll just carry on, because what we want to see is here, it's going to flatten out. And, you know, it'll approach the, you know, if we start off with 0.100 molar sodium, if we're using 0.100 molar sodium hydroxide, then the pH is going to go up to approach 13 as we go up to infinite milliliters of strong base. And so we want to see this flat part of the curve, and this. And so basically, we're looking for what we call the structural features, you know, of the titration curve. You know, this excess acid, the equivalence point. Over here, we have the excess base part over here. Now, the equivalence point is different than the end point. You know, what is the end point of this titration? Do you know where phenolphthalein starts to turn pink? At what pH? Phenolphthalein doesn't start to turn pink until about pH of 9. And so here, if you're looking at it, around here, you know, you're going to start to see phenolphthalein turn pink. I don't have any pink color here. But phenolphthalein changes color. Here, at around pH 9, and so it's pink up here, or red, and then it's colorless down here. And so what you're after, and it stays pink, you know, it just the color darkens a bit. And you think, well, this is called the end point of the titration here. End point of the titration. And you're thinking, well, the end point and the equivalence point aren't the same thing. Well, they aren't. And so the end point, there's a little bit of error associated with that because we're using the end point to indicate where we stop our titration. But there are a couple of things to say about this error here. One, this error here is very small. I mean, the line is almost vertical here. And so the amount of sodium hydroxide is less than a drop. Much less, maybe like a quarter drop, or it depends. I have to do the calculation. But the error is very small. So we say it's practically negligible. And two, this is more of a systematic error because all your titrations are going to be impacted by this. And therefore, if you do some kind of standardization, it's going to be off as well. And so this error doesn't really impact us. But phenolphthalein is suitable for this to indicate the end of the titration here. Now, indicators are interesting because indicators are like kind of like buffer systems. And so let's take a look at indicators really quick. Let me show you. We don't have to use phenolphthalein. There are other indicators that we can use. But some of them aren't going to be very useful. So for example, one of the indicators we might be able to use is something called methyl orange. But the pH that it changes color at is way off. You know, if you have an indicator that changes color down here, it's not going to tell us anything. You know, if pH is below this, it's this color. If pH is above this, it's another color. And so let's take a look at the indicator here and see which ones might be suitable for this particular titration. Well, the indicators are going to be a weak organic acid. And usually we use this for the, rather than calling it A for generic anion, we just call it IN minus for the indicator anion. And some organic acids, so this part's kind of big, and this part is what gives it the color, because H plus doesn't have any color. When we look at the hydrolysis of this acid, we're going to see some equilibrium with its conjugate base, actually, and hydronium. Let's do it the standard way, hydronium plus IN minus. And basically, the indicator, you know, this is going to be the acid color over here, and this is going to be the base color, you know, IN minus, we call the base color. And we can shift between the acid color and base color by changing its pH, the hydronium ion concentration. And so as the hydronium ion concentration goes up, this equilibrium shifts towards the acid color, which makes sense. As we add more hydronium, it should become more acidic and the acid color should dominate. If we get rid of hydronium by attacking it with sodium hydroxide or something like that, you know, this equilibrium is going to shift to the right, giving us the base color. Now, where does that shift occur? That shift doesn't occur at pH 7. You know, it depends on this particular equilibrium here. And so the shift, the acid color, is just relative to its pKa, it turns out. Because if you look at it, what kind of system is this? If we have acid and base in sizable quantities, then we call this a Henderson-Hasselbalch buffer. And it should be described by the Henderson-Hasselbalch equation. That is, pH is equal to pKa of the indicator, acid form of the indicator, plus the log of the IN minus to HIN concentration. So we have something like this. When we have like greater than 10 to 1 or equal to 10 to 1 ratio of base to acid, then the base color dominates. Then we go to the other limit, and that is a 1 to 10 ratio. If we have less than or equal, and then we have what is between these. If we're less than or equal to 1 to 10, that is 10 parts of acid, 1 part of base, then the acid color dominates. If we're between these, let's say between 10 to 1 base to acid or 1 to 10, then what we have is a mix or an intermediate color. Intermediate or mixed color. For example, a 1 to 1 ratio. A 1 to 1 ratio would be 1 part of base to every 1 part of acid. Well, we're going to have a mixed color. Well, we can figure out what the pH is. You know, when we have a 1 to 1 ratio of acid to base, then the pH is equal to the pKa. If we have 10 parts more base, then the pH is going to go higher, and the pH is going to be greater than or equal to the pKa plus 1. And then the acid color here, we're going to have a pH that's going to be less than or equal to the pKa minus 1. So for phenolphthalein, the pK is around 9. If the phenolphthalein has a pK of around 9, then that means at a pH of 9, we have a 50-50 mix of the acid color. Do you know what the acid color for phenolphthalein is? Colorless. And the base color, 50-50 mix, will be a light pink color, right? Faint pink. So that's what we're going to see in that range. And so we should start to detect the faint pink color at around pH 8. Okay? Because around pH 8, we're going to have 10 parts more base than acid. And so we'll start to detect that color around there. And then it's going to become more and more pink. And then when we get to about 10 to 1, then it's going to stay pink. You know, it's enough base that that's all we're going to see is that pink color. And so around pH 8 to 9 is where we want to stop. You know, 8 to, actually 9 to 8 to 10. 8 to 10 is where we want to stop for phenolphthalein. So let's take a look at So let's take a look at some other indicators as well as phenolphthalein. So here you can see, you know, this is weak organic acid colored. A lot of organic acids are colorless. We have the pKa. Let's take a look at phenolphthalein here. Okay, phenolphthalein is shown here. And so from pH, you know, below 0, you see this scale goes negative here. From pHs below 0, it's colorless. Stays colorless all the way until you get to about pH 8, where it starts to change, you know, because there we have enough. So over here we have greater than 10 parts of acid, greater than 10 parts of acid to every part of base. And then when we get here, we get about 10 to 1. And then as we continue on, it gets smaller. We get more and more base. But once we hit about pH 10, then it's going to just stay the same color all the way out to, I mean, this one stops here, but 12, and we'll go all the way up past 14, right? That same color. And so this is really the only part where, well, that's off because, you know, at the equivalence point, our equivalence point is pH 7, so there's a pretty big error, isn't there? There's a huge error in pH. Even though there's a huge error in pH, there's a tiny error in volume because it's near vertical. Well, that huge error in pH, if we had a huge error in pH here, there'd be a huge error in volume because pH doesn't change much here. And so even a tiny error in pH here means a big error in volume potentially here. But a big error in pH here means just a tiny error in volume. We could use other indicators too. For example, thymol blue. Thymol blue would work, you know, because we go from yellow to blue, and the intermediate color here would be green. Mix. That's around pH 8.5, 9. That would work, no problem. That would give us an even smaller error. You know, thymol blue would change around here. Small error. Phenol red. Phenol red looks perfect, you know, because it changes from yellow to red, and the intermediate color would be orange here. And so we'd detect an orange color around pH 7, just slightly past pH 7. In fact, phenol red is probably better. You know, but the problem is why not use phenol red? Because it's hard, you know, going from yellow to red and through this orange is hard to see the colors. You know? It's much easier to go from colorless to colored. Actually, what would be perfect is bromethymol blue. Bromethymol blue goes from yellow to blue, and so it turns green, although this is not a very good green here. It turns green at pH 7. And so bromethymol blue would be perfect. You just look for the green color. And then there would be no error. But since the error is so small, it doesn't matter. I mean, we could go the opposite side here with methyl red. Actually methyl red would work. Because if you look at methyl red, we go from red to yellow, and the orange is going to be around pH 5. Well, pH 5 is no problem because pH 5 is still on this vertical part here. But what if we used alizarin yellow? Would alizarin yellow work here? Alizarin yellow stays yellow and then goes to violet, so there's some intermediate color here around pH 11. Would that work? If it changed around pH 11, then
Should we pass the third?
yeah, it'll be way out here, which means it's not going to work. Nor will anything down here work either, because it's not going to tell us anything. And so these are all indicators, and you can tell what the pKa values are because the pKa's would be right in the center of this. And so this is the pKa minus 1, this is the pKa plus 1. And so this is the range from pKa minus 1 to pKa plus 1 for the pKa. So the number of indicators we could use for this particular titration. Well, this is more of a standard Chem 1A stoichiometry problem. You know, the only difference is we'd set up as a nice table, and then we just calculate the pH based on that. And one other difference is at the equivalence point, or right around the equivalence point, we would need the KW step. But anywhere else, we don't really need the KW step. We have high enough concentrations to avoid it. And so this curve looks like, I'll show you what this curve is. In your book. So this is what this curve looks like. So we saw there's a whole range of indicators we could use, but we couldn't use the alizarin yellow because that's going to be way off. This, you know, we're trying to get the color here. There's going to be a pretty big volume range that color can be. These are all minimal error here. This would be a huge error here. You know, if you look at that range, you know, the top of it's here, the bottom of it's here. There should be a huge error in the volume there. So strong acids start off at low pH. This is starting off at pH 1, and then at the equivalence point it skyrockets, you know, up to about 12. Looks like so we're going from 1 to 12. That's 11 pH units. So this is a huge jump here in pH, which means to catch it you have to be very careful. All right, let's take a look at another titration curve. This one here is the opposite. Basically, this one, you're starting off with the base in the flask and titrating it with strong acid. And so it's just an inverted curve, essentially the same thing. We're going to have excess base initially, and then equivalence point, and then excess acid as we're titrating it. You could titrate either way. This curve here is for weak acid with a strong base. So here we're titrating with sodium hydroxide. This is what, acetic acid? Yeah, acetic acid. And so initially, this is 0.100 molar acetic acid. The pH is much higher, pH around 2 to 3, closer to 3. And then we have the excess, acid. That is, we haven't neutralized it. And then we have the equivalence point here. If you look at the equivalence point should be right in the center. Does that look like right in the center of this? It looks off, doesn't it?
Mm-hmm.
maybe it's because this bar is here, phenolphthalein, but still looks off. The equivalence point should be right in the center. However, the end point need not be. So I think they made a mistake in labeling this. This should be labeled the end point, not the equivalence point. The end point is where the indicator changes color. This is where the indicator changes color, it's phenolphthalein. The equivalence point, I would pinpoint it just slightly lower here. And so you can see with phenolphthalein is an excellent indicator for this because it's quite close. And the reason is because we are making a neutral salt and water. We're making sodium acetate. Sodium acetate is what we call a basic salt. And so sodium acetate has a pH of higher than 7. So this works well. And then we're in the excess strong base. And so let's take a look at this titration calculations for this one. First. So the regions that we have for this one, this will be a weak monoprotic acid plus strong base. Okay, the first thing is the pH is going to be higher, like 2 to 3 range, let's say. And then this curve goes, and it's pretty flat actually. This, after we do step 1, step 1, strongest acid plus strongest base, then we're left with step 2. And so we label this based on step 2. Step 2, turns out it's buffer. As we're going to have excess acetic acid plus product. The product of this neutralization is sodium acetate. And so here we're going to have HAC and sodium acetate as the product. Well, HAC and sodium acetate, that's a Henderson-Hasselbalch buffer. And then as we get closer to the equivalence point here, the pH rises rapidly again, and then over here at the equivalence point, we're going to have sodium acetate and water. Well, sodium acetate, again, this is a base. This is base. The acetate is base, so the pH is going to be higher. And so we're going to see a pH greater than 7 at the equivalence point because it's a basic salt. And then once we go past that, then we have excess sodium hydroxide left over. And so what we're going to have is we're going to have excess sodium hydroxide and sodium acetate. And so this is what we call strong base, weak base solution. Well, if we have a strong base, weak base solution, then typically just the strong base dictates what the pH is, unless we're very close to the equivalence point. When we're very close to the equivalence point, we have to do additional steps like KW. But outside the equivalence point, we don't really worry too much about KW. It's not really going to impact them. And so we do a number of calculations for this, and I'll do some standard calculations first, and then we'll look at some other points. And so the standard calculations, we want to calculate the pH, initial pH, and then we want to calculate the pH at the half equivalence point. And then we're going to calculate the pH at the equivalence point. And then we're going to calculate the pH at the 1 and 1/2 equivalence point. 4. Okay, after we do these, then we're going to calculate some more, do some additional calculations in here. So, for example, we're going to do some calculations in here, 5, etc. Be in different spots of the titration curve. And so we're going to do these calculations just to put some numbers on the curve. Why is this shutting down? Okay.
number one right there where the HAC plus NaAC, that would be the weak acid and the weak base.
Again, somebody's logged into this remotely. It's weird. All right, we'll skip that.
All right, so let's do some calculations here. We're gonna put some numbers on this. We're gonna just do the same one that was on the board. So we'll pick 0.100 molar acetic acid and 0.100 molar sodium hydroxide to keep the numbers simple. And then what we'll do is we're gonna titrate, let's try to keep this simple. We're just gonna titrate 10 milliliters of acetic acid solution. And so basically we'll just put some 10 milliliters of acetic acid in the flask. This. And then titrate it with the sodium hydroxide in a burette. And so let's start off with calculation one. Calculation one is with 0 milliliters of sodium hydroxide. And so all it is we just have 0.100 molar acetic acid. And so we just need to figure out the pH for that. And so acetic acid reacting with the strongest base would be water. That gives us hydronium and acetate. Initially, 0.100 molar here. Is this a buffer? Can we use the Henderson-Hasselbalch equation for this? Is this a buffer?
Yes.
No. This is not a buffer. Why? A buffer has to be a mixture of weak acid with weak base. Is this a mixture? You know, you need both acid and base present because the buffer has to be able to neutralize both added acids and added bases. If we add HCl to this buffer, what's going to neutralize it? Nothing. I mean, we have acetic acid. Acetic acid is not going to react with HCl. This is not a buffer. How about this? If I change the acetate, now 0.100 molar acetate, is this a buffer? Yes, this for sure is a buffer because we now have a mixture of both components, and that constitutes a buffer. Well, where did the acetate come from? Well, it didn't come from anywhere. There's no acetate in here. I would have to add it physically in order to make this a buffer. I don't have it, and so this is not a buffer. This is just a weak acid solution. Change, so at equilibrium I have 0.100 minus x, x, and x. We use the simplifying assumption, Ka for this acid is 1.8 times 10 to the minus 5. So actually, did I bring my calc? I have a calculator here. All right, so I think we could just do the square root of 1.8 times 10 minus 5, if we use the simplifying assumption.
So square root of 1.8 times 10 to the -6, because you multiply it by 0.1.
Oh, yeah, thanks. 1.8 times 10 to the minus 6, which gives us an x of
1.34 to the -3.
So this is 1.3%. 1.3% is okay. So are we going to worry about the hydronium from water? No. So we don't worry. And so let's get the pH. pH is equal to a negative log of that.
Professor,
Mm-hmm.
how come we don't worry about the hydronium?
What's the most hydronium we're going to get from KW? The absolute most. Will -7 have any impact? Even if I add 1 times 10 to the -7, is that even going to register on this? No. When I round it to the correct number sig figs, it has no impact on it. Therefore, we don't worry about KW. That's how I determine. I determine it just by looking at how big this concentration is. If the concentration's big, don't worry about it. If the concentration's small, you better worry about it. So pH comes out to what?
2.87.
2.87. And so I was going to show the curve, but it's all right. We use this curve here. pH is 2.87. Actually, I'm allowed 2 sig figs. Give me one more digit.
3.
2.873. So the initial pH here is 2.873. All right, then let's go to this where I've added a half equivalent. Now, note the concentrations are the same. So if I have 10 milliliters of acetic acid, how many milliliters of sodium hydroxide will I need to neutralize that? It's the same concentration as a 1-to-1. And so at the equivalence point, I need 10.0 milliliters of sodium hydroxide to neutralize 10.0 milliliters of acetic acid of the same concentration. And so that's the equivalence point is 10 milliliters. Half of that would be 5. And so at 5 milliliters, 5.00, if we give 3 sig figs, that should be half the equivalence point. That is half the amount of acid required. And so this is with 0 milliliters. And so the next calculation, let's go over here, we're going to do with 5 milliliters. And wow, I don't know what is wrong with this. Let me see if I can disconnect it. Internet. All right, so the next calculation is with 5.00 milliliters of sodium hydroxide. And so what we have to do is we have to do a solution dilution, because if we start off with 10 milliliters of acid and we add 5 milliliters of sodium hydroxide, what we're going to be left with is 15 milliliters of mixture. Okay, so we want 3 sig figs. So we'll go with 15 milliliters mix. Now, what we're going to do is we're not going to do the reaction just yet. We're going to figure out the new concentration. So if we have acetic acid, it's no longer going to be 0.100 molar. The acetic acid is going to undergo dilution. So we start off at 10, we dilute it to a total volume of 15.100 molar. And so what is that dilution factor?
Why aren't we using the equilibrium concentration of acetic acid?
Why aren't we?
Yeah.
Because it's easier to reset. With each of these calculations, we reset to the beginning rather than build up on the previous calculation. Otherwise, it becomes a total headache with the calculations. And so, yeah, we have this. We could use the equilibrium. It's just like KW. You know, why are we having water at 0? You know, hydronium or 0 hydroxide? Because, you know, if you put in 10^-7 there, it's going to be changed anyway. If we put this in there, it's going to be changed anyway, so why bother? Just reset it and start over again. And so we start over again. This is going to be a 10 to 15 dilution, which is what? I should have picked easier numbers.
0.066.
All right, 2/3. Yeah, 2/3. 0.0. Now we have 3 sig figs, so I'm not going to round. I'm just going to call it 0.0666 molar. And then the sodium hydroxide is going to undergo dilution too. The sodium hydroxide is going to be a 5 to 15 dilution, which is a 1 to 3 dilution of 0.100, which is going to give us 0.0333 molar. We don't want to round this because rounding. Now your book does something different than what I do. I always do solution dilution, but what your book does is they convert it to moles. You know, react the moles. Moles are a hassle. They use millimoles since we aren't dealing with that many moles. You could do either, but I'm going to stick with this in the solution dilution because, oops, no, forget it. I realized I did unplug the network cable, but I have to get my stuff. All right, so what's the first step? And the first step in all our problems is we just take the strongest acid, react with the strongest base. I'm going to erase this chart. So I need the room. And we'll just use the one on the projector. Figure out where we are. And so step 1, what's the strongest acid present? So this I called step I. You know, we're going to be doing step I initially. Step I is this solution dilution. And this is our initial step. And then finally we'll let the reaction occur. So the strongest acid present, the strongest base, sodium hydroxide. This is going to produce sodium acetate and water. What's K for this? Reaction.
And Professor, this is still at the half equivalent point.
Half equivalence point.
It's very, very strong.
K for this is what?
Very, very,
Very large. No, not exactly. Close, but not very large. It should be.
It's pretty very large.
Yes, it should be just very large. Because the last one was HCl. HCl is much stronger acid than acetate. And so this has got to be smaller than the previous one. And so to indicate it's smaller than the previous one, we'll just call it very large rather than very large. Very large we reserve for reaction with water. And so we can just plug in, now we have the diluted concentrations of the mixture. And so the acetic acid is 0.0333.
oops, no, I got it wrong. Acetic acid is an excess, 0.0666 of 6 molar, 0.0333 sub 3 molar, and 0 molar. And so this reaction should go to completion, strong react to completion. And so the limiting reagent here is sodium hydroxide. And so we're going to end up with 0.0333 sub 3 molar acetic acid, 0 molar sodium hydroxide, and 0.0333 sub 3 molar sodium acetate. Okay, after step 1, we look at what we have left over, and usually we repeat. You know, after step 1, we repeat with what's left over. We take the strongest acid that's left over and react it with the strongest base. If you take the strongest acid, that would be acetic acid. Now we don't have any more sodium hydroxide left. And so the next strongest base would be sodium acetate. But acetic acid plus sodium acetate, is that going to yield any reaction? No. And so then we think about Ka and Kb. Maybe we do Ka for acetic acid or Kb for sodium acetate, because that would be the next, right? But you should recognize this. Do you recognize this right off? We don't have to do any of that stuff. We did that, you know, spent almost a full period doing that, wasting time. It was actually a wasted time. It's a wasted time to show that lots of people do end up wasting time unless they recognize this solution, this mixture right off as a. No, this is not simultaneous. You don't need simultaneous for this. You should go back and review those and see, because if you can recognize these things quickly, it saves you a lot of time on the test, you know, rather than going in circles like we were doing earlier. This is a Henderson-Hasselbalch buffer. And so step 2 is very easy. I'll call it HH buffer. And so this is why we call this region of the curve the buffer region. It's a HH buffer. This one is not an HH buffer here because this is strong acid, strong base. And so we just have excess strong acid, HCl and sodium chloride. Well, that's not a buffer. But this region here is what we call the buffer region. Because here the excess acid is acetic acid, and then we have the salt, sodium acetate. We have excess acid, salt, sodium acetate. And if we use the Henderson-Hasselbalch equation here, then what we're going to get is the pH is equal to the pKa of acetic acid plus the log of the acetate to acetic acid concentration. Well, what is,
To recognize H and H buffers, like the conjugates, they just have to share the same anions, but they only have to be like one H, like plus difference. Like,
Yeah,
that's
right.
all it is. It doesn't matter like the cation for the
no,
base.
no, they just have to be a conjugate pair. They could be anything, yeah. It doesn't matter.
So step 1 is a buffer because acetate is the weak base and then acetic acid is the weak acid?
It's not step 1, step 2.
Oh,
Step 2. Step 1 is always the neutralization reaction. And so step 1 is, you know, neutralization. What you end up with after step 2 is a buffer. And so this is why we call from here up to here, this is the buffer region. Now buffer should be flat, you know. And so here, what's the pKa of acetic acid? So that would be the negative log of 1.8 times 10 to the 1.8 times 10 to the, actually I'm not familiar with this calculator. Well, here it is, yeah. 10 to the negative 5. 4744. So 4.744 would be the pKa plus the log of 0.0333 0.0333 sub 3 over 0.0333 sub 3, which is 1. Log base 10 of 1 is. And so, in other words, at the half equivalence point, the pH is equal to pKa. And so this is what they're showing here. At the half equivalence point, the pH is equal to pKa. So they figured out what the equivalence point is. The equivalence point is at 25 milliliters. So half of 25 milliliters would be 12.5 milliliters. At 12.5 milliliters, the pH is equal to pKa. Now for a Henderson-Hasselbalch buffer, we want the buffer range to be pKa plus or minus 1. And so if we go pKa minus 1, that's 474 down to 374. And so we go down to 374, which is about here. And so that's pKa minus 1. pKa plus 1 is 474 to 574. So 574 would be here. And so we call this the buffer range, right? Because Henderson-Hasselbalch buffer should be within a pH of pKa plus or minus 1, which gives us, this is a 10-to-1 ratio of acid. This is a 10-to-1 ratio of base over here. If we go, we'll get more base than 10-to-1. If we're over here, we get more acid than 10-to-1, or 1 to 10, or whatever you want to call it. However, just because this is the effective range, the pH, pKa, that doesn't mean we can't use the Henderson-Hasselbalch. The range that we can use the Henderson-Hasselbalch actually is wider than this. It's just to make a practical buffer, you want it 10-to-1 or 1 to 10. So you have a decent capacity to neutralize both added acid and added base, but for the Henderson-Hasselbalch to work, all that has to work is a simplifying assumption. And there you just need decent concentration. So the Henderson-Hasselbalch equation can be used for calculations almost from the start here to almost the end. But as we get closer to the end here, it becomes too dilute, you know, I mean, too dilute in acid and too much sodium acetate. And so we have to start using regular ice calculations there. All right, now we're going to do some other calculations in the buffer region, and there's a shortcut way of doing the calculations. So what number is this, 2? Okay. Now, we're going to do 2A, 2B, 2C, 2D. This is all in the buffer region. And so let's do 2A. Now, we're going to start this calculation over again. We had 10 milliliters here as our equivalence point. The half equivalence point was at 5 milliliters. And so we're going to do the 1/4 equivalence point here. And so that was the half equivalence point. Now 2A will do the 1/4 equivalence point. The 1/4 equivalence point would be plus 2.5 milliliters of sodium hydroxide. And so if we start over again, at step I, we're going to have, rather than 15 milliliters, we're going to have 12.5 milliliters. We have 12.5 milliliters. Let's recalculate the acetic acid concentration. This is going to be a 10 to 12.5 dilution of 0.100 molar. And so what does that equal? And so 10 times 0.1 divided by 12.5. This is 0.00800. Then we calculate the sodium hydroxide concentration. The sodium hydroxide concentration is going to be a 2.5 to 12.5 dilution. Keep it 3 sig figs of 0.100 molar.
Professor,
Mhm.
why do we have to find the pH within the buffer region? What's the point of that?
What's the point of that?
Yeah, of finding the pHs within the buffer region.
Point of that is so we can map out the curve. You know, so for example, where is the curve? Here. You know, if I, the point of this is being able to predict. If I add 2.5 milliliters of sodium hydroxide, can you predict what the pH is going to be?
Yeah, we can predict it. That's what we're doing right now. So the point is to be able to predict what the pH is going to be. In fact, the point is to be able to calculate this whole curve without actually having to do the titration. Then that's kind of nice to be able to do that. And so we'll do that, and then so 0.25 divided by 12.5, 2,000. All right, what's the next step here? The next step is we take our strongest acid plus our strongest base, and then react them. This is going to give us sodium acetate and water. Okay, then we do this. The HAC is going to be 0.0800, 0. The sodium hydroxide is 0.0200, 0. Sodium acetate, 0. We change limiting reagent sodium hydroxide, that's going to go down to 0. This is going to go 0.600, no 600. This should go 0.200. And then what are we left with? We're left with a HH buffer. So we're left with an HH buffer. We can calculate it. The pH is equal to the pKa plus the log of the base, which would be 0.200, over the acid, which would be 0.0600. I'm just going to do this in terms of pKa, and so let's take 0.02 divided by 0.06, and I'll take the log of that. 0.47. This is going to be the pKa plus the log, oops, not plus the log. pKa minus 0.477.
For log, where did you get the 0.200?
Oh, 0.0. Sorry, this should be 0.020. That came from here.
Professor,
Mhm.
when we're reacting with strong acid and strong base, would that be at the equivalence point?
Would it be at the equivalence point? No. It doesn't have to be at the equivalence point. We could be, when we're reacting with strong acid plus strong base, depending on the stoichiometry, it could be anywhere on this curve. In fact, this is all we're looking at. You know, the calculation, this is all the same stuff. This is, you take the strongest acid, react it with the strongest base. You can solve this. You can solve any point on here with the setup we already did. What we're learning right now are shortcuts. Because if you just do ice table 1, you know, you have to do step I, but otherwise all the calculations are exactly the same. And so rather than doing each calculation the exact same way, which just takes time, it's no big deal. You could do it, every calculation exactly the way we've been doing all the calculations up to now. What we're learning right now is how to do some rapid calculations to do these quickly. Now, in the buffer region, this is considered slow. This is a standard calculation. Any point on this curve can be calculated using a standard calculation like this. It doesn't matter if it's in the buffer region or outside the buffer region. Don't do this again, please. Or wherever. Okay. But what I'm going to show you is even this is, you know, first we recognize the Henderson-Hasselbalch. You know, that saved us a lot of time. Because if we didn't, we'd either have to do a Ka or Kb as the next step, right? And we'd have to recognize that K and Kb are the same thing. And so the Henderson-Hasselbalch was a huge time saver right there. But there's even bigger time saver. Any calculation in the buffer region can be done much quicker. In fact, I don't even set up an ice table. If it's in the buffer region, I just can do a very rapid calculation. Let's see. So we're going to do 2A. You know, so we already saved time by skipping the additional ice tables here, but we can skip even more time by skipping this ice table entirely, and we can do that only in the Henderson-Hasselbalch region. In the Henderson-Hasselbalch region, let me show you the quick way to calculate this.
So this would be an alternate 2A.
In fact, we'll just stick with this method from now on in the buffer region because this is it.
And so, well, I'll just set it up. This is just to show how this works. So, basically, we have some amount of acid here, and we have some amount of base, and then this base, you know, we have excess acid, you know, and this base is the LR here, the limiting reagent. And this is going to translate into product, this product here. And then we're going to consume this, you know, this is going to be minus the LR here, and then we're going to get some acid over here. And so what this means is this. At the 1/4 equivalence point, then I have, let's say this is my excess, then I'm adding 1/4 equivalent of limiting reagent. That means that's going to be converted into product. And that means I have 3/4 of acid left over. Do you see that? And so this gives us a rapid way to do this because I know I'm in the buffer region. So after step 2, after step 1, I just have a Henderson-Hasselbalch. And so I do this. The pH is equal to the pKa plus the log. Now what's the ratio going to be at the end? The ratio is going to be 1/4 over 3/4. This is what we call the 1/4 equivalence point. And so 1/4 converted to product, 3/4 left unreacted, right? Remaining. This is the excess remaining. Well, that's just equal to the pKa plus the log of 1/3. The log of 1/3 is just minus 0.477, so this comes out to pKa minus 0.477. Okay, let's do another one. Let's do alternate 2. We'll repeat the calculation where we did this. So we start off with some initial amount of HAC, and this is HAC, and then we don't have enough NaOH, you know. We only have 1/2 the required amount, so that would be 1/2 the concentration of our HAC, right? And so what's this going to lead to? It's going to lead to 1/2 of the converted into product, right, here. And then we'll be left over with 1/2 unreacted acid. Moving out the stoichiometry. So this is HAC, that's HAC. So the pH at the half equivalence point is just going to equal the pKa plus the log of 1/2 converted to product, 1/2 remaining. Well, 1/2 over 1/2 is just equal to 1. So the pH is equal to pKa.
So sodium hydroxide goes to completion?
Yeah, sodium hydroxide always goes to completion. It goes to 0. Okay, so let's do some new calculations now. Let's do 2B. We're going to just use this method to do it. We go to the 3/4 equivalence point. At the 3/4 equivalence point, the pH should equal the pKa plus the log of, now 3/4 equivalent, that means I've neutralized 3/4 of it, so I convert it to product. Here, that means 1/4 is left over, right? And so what I end up with is I got the pKa plus the log of 3. The log of 3 is plus 0.477, so this is the pKa plus 0.477. And so it's very quick. These calculations are very quick, so we can figure out this buffer region and map it out extremely fast, because at the 1/4 equivalence point, I have pH is equal to the pKa minus 0.477. At the 1/2 equivalence point, I have the pH is just equal to the pKa,
And at the 3/4 equivalence point, I have the pH is equal to the pKa plus 0.477. And so these require minimal calculation to get. There are additional ones. Actually, we could get any point in there that we want. And so let's do some other ones that are going to so for example, if I want the 1/10 equivalence point or the 9/10 equivalence point, that would be easy, right? The 1/10 equivalence point, how would I do the 1/10 equivalence point? And so we'll do the 1/10 equivalence point, is 2C. That means I've only neutralized 1/10 of my acid. And so that means the pH is equal to the pKa plus the log. So 1/10 of it's converted into product, that leaves 9/10 behind. And so this is equal to the pKa plus the log of 1/9. Log 1/9.
Professor, for is the Hasselbalch, is the Henderson-Hasselbalch region also the buffer region?
Yes. So this is log 1/9. We can figure that out here. 1 divided by 9. Take the log of that. 0.95 minus 0.95. So this is equal to pKa minus 0.95. Now, the Henderson-Hasselbalch region has a couple of important points. And so we could go the opposite direction. For example, we want the pH to equal the pKa minus 1. If we have the pKa minus 1, then we know we have a 1:10 ratio base to acid. 1:10 ratio, right, to give us a minus 1 in the log term. And so how many milliliters? The question would be, how many milliliters is that? How many milliliters of sodium hydroxide? And what is the equivalence point? So if we have a 1:10 ratio of base to acid, this is base to acid, does that mean I'm at the 1/10 equivalence point? It is not equal to the 1/10 equivalence point. We just did the 1/10 equivalence point. The 1/10 equivalence point is a pKa minus 0.95. So this is not the 1/10 equivalence point. Do you know what the equivalence point is? This? All right, that's what we're going to figure out. And so what we're going to do is we're going to work kind of backwards here. And so we know what the pH should be. And so we want the pKa now plus the log of this. What we want is we want 1 part of acid for every 10 parts of base. Right? So how do we get that? How do we end up with that? Because that's got to be the after step 1. And so what we have to do is we have to take our ice table and work backward. You usually do this in your head, but I'm going to do this on the board for the first time, and then after this we'll just do this in our head or via simple calculation. And so by the end of step 1, we want 1 part of base to 10 parts of acid. So we need 10 here and 1 of whatever our original concentration is. Sodium hydroxide is going to be 0. Now you have to work backwards. What was the initial? If we end up with 10 here, then how much did we have initially? If we end up at 10 at the end of this ice table. 11. 11's correct. We must have started off with 11 parts of acid. And how many parts of sodium hydroxide? 0. And so this has got to be
we must have had 1 part of sodium hydroxide here, and so this is minus 1 part of sodium hydroxide, it's 1 part of sodium hydroxide plus 1 part of sodium hydroxide. So 11 minus 1 gives us 10, 1 minus 1 is 0, and 0 plus 1 gives us, and this gives us a 1 to 10 ratio of base to acid. And so what we call this is we've neutralized 1 part out of 11. 1 part out of 11 is called the 1/11th equivalence point. And so this is the 1/11th equivalence point. It's got to be the 1/11th equivalence point. And so at the 1/11th, we could see that here because this is the other way I could have done it without generating that. 1 plus 10 is equal to 11. So 1/11th has been converted to base, and 10/11ths remains. And the 11th cancels, and then we're left with 1/10 ratio. This is going to give us pKa minus 1. The 1/11th equivalence point. Well, how many milliliters is that? Well, how many milliliters that is this calculation. The equivalence point is, so it's 1/11th of the equivalence. The equivalence is 10 milliliters. We need a full 10 milliliters for the equivalence, and we've only done 1/11th of that. And so this comes out to 0.09. It's 1/11th, 10.
Are you using like a dilution factor to do that, or what are you doing?
0.909. 0.909. Or 0.909, sorry. Am I using a dilution? No, I'm not using dilution. I don't worry about dilution factors here, but in the buffer region, I don't have to worry about dilution. I don't do any dilution. I just go straight. This is a shortcut calculation.
So why are you working backwards? I mean, when you did the ice table.
Why I work backwards is because I need to figure out how many milliliters this is going to take. In order to figure out how many milliliters, I need to know, am I halfway there? Am I 3/4 of the way there? Where am I from 0 to 10 milliliters? If I go to 10 milliliters, that's called the equivalence point, 100 out of 100. And so where am I in that range? So that's what I'm using that for.
And for the top part too, when you did the 1/10 ratio, how is it not equal to 1/10 equal within?
The equivalence point?
Yeah, the equivalence point.
Because at the 1/10 equivalence point, we have this. 1/10 remaining, 9/10, this amount. 9/10 remaining, 1/10 reacted. So let's do the same thing for that. If I look at the 1/10 equivalence point, I've neutralized 1 part out of 10. So I start off with 10 parts. I neutralize 1 part. I'm going to get rid of the other thing. This is going to form sodium acetate, which is 0 parts to begin with, in water, which we ignore. And so the limiting reagent here is sodium hydroxide, so I'm left with 901. And so this gives me, when I look at the pH is equal to pKa plus a log of 1/9. So the point of doing this is that this ratio here is not the equivalence point. In order to determine the equivalence point, you have to add the two together. That's 10. So 1 out of 10 has been converted, and 9 out of 10 remain. This is the equivalence point. This is what we call the equivalence point. This is not the equivalence point. And so we have to do an additional calculation to get the equivalence point. Why do we want the equivalence point? Because that's going to tell us how many milliliters are required to get here. That's why we want it. And so we could do any other point on this that we want. Did you have a question?
Oh yeah, right there, the milliliters equals 1/11. Can you go over what that means, like what you were doing?
Okay, how many milliliters is this going to take? So the 11th out of 11, what you do is you divide this. You divide the x-axis. So from here to here, this is one equivalence. And so over here, this is the equivalence point. We've neutralized it all. And so all we did was we divided, and so we're at the 11 out of 11th equivalence point, we're at 10 milliliters, because we had 10 milliliters. And so if we're at the 11 out of 11 equivalence point, well, 11 out of 11 of 10 milliliters is 10 milliliters, so we're at 10 milliliters, right? However, if we're at the 1/11th equivalence point, how many milliliters is that? Well, that's 1/11th of 10 milliliters, because 10 milliliters would be the full amount required, so what was 1/11th of that? And so that, the half equivalence point would be, 5.5 out of 10, 5.5 elevenths out of 10 would be 5 milliliters. You see? And so it depends on, this denominator changes depending on what, and so we just adjust it and normalize it to 10 milliliters. That's all we're doing. Let me give you another example here really quick. The next example is, okay, I want to get to a pH of 5. So this would be 2, whatever. So we want a pH equal to 5.00. How many milliliters of sodium hydroxide will that require? Well, the first thing is a pH of 5.00. Is that in the buffer region? Yeah, the pK is 474. This is in the buffer region, so that makes the calculation much easier. And so this is a Henderson-Hasselbalch problem. So pH, we want it 5.00. This is going to equal the pKa 474. So 4 plus the log of the acetate to HAC ratio. Subtract that from both sides. And so we get the acetate over HAC ratio is equal to 5 minus 4.74, 4. Take the log of that. Minus 0.59. I think that's right. Is that right? Yeah. Okay. So, so I have a ratio. Well, 0.591. This is 0.591 over 1. So how many milliliters do I need to get here? 0.59 milliliters? How many milliliters? I could set up an ice table like this if I wanted to, but I don't want to, because I can do it much faster in my head. But what I need here is I need a ratio of 0.591 parts of base to every 1 part of acid. This is the ratio that has to be at the end of step 1. What was the ratio at the beginning?
Actually, I don't think it's a 0.591.
All right, what is it?
I think you took the log of 0.26, but you're supposed to
Take the anti-log?
Yeah.
Oh. What does it come out to?
1.81.
Okay, I'm not good with this calculator here, but thanks. 1.81?
1.82.
Look, don't round it though.
Okay, 1.81.
Okay, 1.81, we'll just do that. So this is 1.81 to 1. How many milliliters do I have to add? Well, this is not telling me how many milliliters. This is just telling me what the ratio is at the end of this. At the end of this, I have 1.81 parts of base to every 1 part of acid, which means that I must have started this with how much? Yeah, I must have started this with 2.81 parts of acid and 1.81 parts of base. And so I'm only neutralizing 1.81 parts out of 2.81. And so this is what we call the equivalence point. I have 1.81 parts out of 2.81 equivalence point.
And so what I'm calling this now is I'm calling this 2.81. So if I'm at 2.81 out of 2.81 parts, then that's a full 10 milliliters, right? But now I'm only at 1.81 out of 2.81. If I'm only at 1.81 out of 2.81, well, what is that? So we just take that, multiply it by our 10.0. And so this is going to be 1.81 times 10 divided by 2.81, which gives me 6.44 milliliters. So it's 6.44 milliliters. I'm allowed, how many, 6.441 milliliters. At 6.441 milliliters, 6.441 milliliters, I should have a pH of 5.00. This is what we're doing. We're doing these, otherwise you're going to be working with ice tables and doing it backward. You can't always work with ice tables, it just takes so much longer.
How do you know the starting concentration of acetic acid is 2.81?
Oh, we just work backwards. Here. This is 0. And so this is question mark, this is question mark. Minus, plus. Minus x, plus x. We know what x is. X is 1.81. Therefore, this must be 1.81. And then working backwards here, this has got to be 2.81. That's how we figured it out. But, you know, eventually you don't even have to set up the ice table. Eventually you just do these in your head and then come up with the ratio in the Henderson-Hasselbalch, saving additional time, not doing anything.
And also for the ratio, the 1.81 over 1,
Mhm.
it would be over 1 for the acids because we're looking for the base.
The base is 1.81 parts, the acid is 1 part at the end of step 1. What was it at the beginning of step 1? That's what we need to know, because once we know what it was at the beginning of step 1, then we know the equivalence point.